time I cleaned up this, we don't need the arrows anymore. Tau 1, we calculated to be 600 approximately S. Tau max we still don't know. We will need it, as we'll see shortly. Tau 1 divided by 2 on both sides, and tau max we put this here is 2. Clean up this. We now have to look at what the maximum tau stress. Now we don't, even though this is tau max, we don't actually know that it's the maximum tau for the cross section. So we have to calculate what tau actually is. So tau max equals S Q max over Ix, and T here is 2. This is equal to S times Q max. Q max is, I erased Q1, so we'll do it again. 5 times 1 plus, so it's 5 times 1 times 5 here. And then this is 5 times, 5 times 2, 2 times 2.5. How do you want to calculate that for me? Or actually, you can just calculate the whole thing.
I'm currently also writing things down.
Okay, I'll do it. We get times 5 plus 5 times 2.5. And this is times, this part of it up here is times 10 to the minus 6, because it's centimeters to the third, and this is times 10 to the minus 10, because there's 4 and there's 2. Okay, this we get is also approximately equal to 600 S. It's the same value as 595.8. So we now know this. Now we don't need this anymore. Now, in terms of the maximum tau for the cross section, so the maximum tau in terms of just shear is 600S, whichever one you want to choose from. It's not really relevant. However, there's also a tau stress caused by the torsion. Now, the torsion, we never actually put the reaction in here. 5PA, 5PM. This is P, and then there's a torsion here. This is looking at the front. And since the shear center is out here on this drawing, okay, it's going this way, it's going that way, that's in. So the reaction here is torsion like this of P times the distance here. The distance here is E, 1.5 centimeters. So that's the torsion. To calculate now what the torsional stress is, which is also a tau stress, which means we add them together. Tau max torsion is equal to, based on the torsion charts for attachment to us, MT, which is the torsional moment, which is P, times T max, the maximum thickness, over J or I equivalent. J equivalent is equal to 1/3 times the sum of EI, TI to the third. In this case, it's 1/3 times these two, so 2 times. The T is the thickness, B is just the length. Doesn't make a difference what orientation it's in, because this is polar. So we have 2 times 5 times 1 to the third,
Let me know, I
Plus-
can't see what you're doing at all.
10 times 2 to the third. That's 1/3 times all of that.
Wait, is that J equivalent?
J equivalent or I equivalent.
What's,
It's also in units of centimeters to the fourth.
Could you repeat just your calculations of that?
Okay, J equivalent. It's VI/TI to the third. B is the length, T is the thickness. So for these two, it's 5 times 1 to the third, and for this one it's 10 times 2 to the third. And this is all divided by 3. So we have 2 times 5. That's 90. So it's J equivalent is 30 centimeters to the fourth. So when we plug in this, we get P times 1.5 centimeters times 2 centimeters, T max, maximum thickness, divided by 30 centimeters to the fourth. We calculate this out.
Let's set the table.
1.5 times 2 times 10 to the power of -4 divided by 30 times 10 to the power of -8. We get the calculation. Sorry. This is not 1.5. I made a mistake here. Because
this is separate gravity.
no, it is 1.5. Sorry, it is. I was thinking something else. Never mind. It would be 1.5 plus. It would be E plus G if it was acting through a center of gravity, but I defined it as acting through this axis, so it's just 1.5. This is equal to 1,000 P.
And T max is just the thickest.
T max is the maximum thickness.
What did that have to do with anything?
This is a torsion. This is nothing to do with shear. This is back from the torsion charts if you want to take a look at them. Now here we calculate T max is 600 S. S here is still P because we don't have like 2P in the shear diagram or anything. Even if I had another P here, there could be a 2P here, which we're not dealing with. We're only dealing with the 1P for this question. I could throw in another P, but we're not going to do that now. So that means this tau max is also equal to 600 P, because P is S. That means the maximum total torsion, I'm going to erase this. This is shear, and this is tau max torsion is equal to 1,000 P. Alright. Now I can erase that here. Tau max total is equal to tau max from shear plus tau max due to torsion. This is equal to 600 plus 1,000 P. And this is equal to our tau allowed, which is 200 megapascals. times 10 to the 6th divided by 1600 is 125 kilonewtons exactly. Now, this isn't, and this would be P allowed due to tau stresses. However, we're not done yet. In terms of just tau, that would be it. If the question only asks tau, that would be it. However, we're also given a bending sigma stresses. So I'm going to move this up here so I can work down here. P allowed due to tau is now equal to 125 kilonewtons, and I can erase the shear diagram. We're done with that. The bending moment diagram is where the shear comes in, is where the sigma comes in. Okay.
And also where E comes in.
No, E actually doesn't come in at all.
So this could hypothetically be for any.
This is for any E. It doesn't make a difference. Material is not relevant.
How does that make sense?
E is only related to deformations. E has no relation to stress. Stress is a function of the shape. E is only what is E? Go back to
the material.
You have
modulus.
Right, it's the Young modulus that relates to this, right?
Yeah.
Okay, well, we don't care about this because I'm not talking about lengthening and I'm not talking about bending.
Okay.
I mean, I am talking about bending, but I don't care how much it bends. I'm just talking about what the stresses are. So E is only related to that. And same thing with G. I technically, I can give you a G is equal to whatever else, and it's still not relevant because it's only related to what the value of the deformation is. Okay. We now have to find what P allowed due to sigma stresses is. Okay? Now, I can erase all this. This is no longer necessary. We already found all the shear stuff. What we're left with is this. Now, on this cross section, let me draw this a little bigger. Not quite that. Because this is symmetric in terms of this axis, the bending stresses caused this way, caused by the top here coming out and the bottom here going in, because this would be bent down, that it would look like that. So our sigma stresses look like this. They're centered around the center. So now which one is positive, which one is negative?
Doesn't matter.
Well, it does make a difference. In terms of sigma top and sigma bottom are going to be equal because this is symmetric. Because it's going to bend down, this is positive. So the top is positive, the bottom is negative, because the top is going to be in tension. Now, sigma max, or sigma top in this case, which is equal to sigma bottom, so that doesn't really make a difference, is equal to the MB, the bending moment, times Y max over IX. Now Y max is measured from the center of gravity to as far as we can get. In this case, it doesn't really make a difference which way we go. It's still 5 centimeters. So,
sigma top equals.
and MB is the bending moment, is 5 p meters times Y max is 5 centimeters over IX, which is 417.5 times 10 to the minus, or centimeters to the fourth. Yeah.
What's the units on the first 5?
The 5, it's 5 meters times p.
Right.
Okay, because that's the moment caused by this. Okay, so with this we get 25 times 10 to the power minus 2 divided by 417.5 times 10 to the power So this is equal to, I'm going to do it up here because I need the room to do the last step. This is equal to 59880 P, and this, which is now what I'm dealing with, is equal to our sigma allowed, 160 megapascal. Doesn't make it was positive or negative. From this we get P is equal to 160 times 10 to the power of 6 divided by, that's unit, well, not unitless, it's meters to the minus 2. So you get P is equal to, and no, this is not wrong, 2.672 kilonewtons. Not very much. Yes, that is what it turns out to be. So now out of these two,
Which is the smallest?
which is the smallest, 2.672 kilonewtons or 125, turns out to be this one. So all the work we did for shear center was sort of worthless, but part of the example. We found P allowed.